for WW, at the threshold for Higgs Z production, and at the TTBAR threshold. And these could be followed by a PP collider at 100 TeV, and in addition, the option of having electron-proton collisions at the center of mass of 3.5 TeV. All of these in a 100-kilometer tunnel around CERN. And there is a similar project. It's not called FCC, it's called CEPC, but it is a future circular collider. And everything I will say focuses on the physics potential of these machines. So in principle, it's equally applicable to the physics program of the CEPC and its own follow-up, which would be a PP collider. And you will have a talk by Jie Gao next week. So I collect here some references to where you can get more details on the physics of the FCC. And let me start by just putting the project in perspective. A question that is often asked is why do we need another collider? We saw the Higgs, we're done. These machines are extremely expensive, but they have a time scale which is many decades. Are we not better off investing our money and our time in smaller facilities with a more focused task? There is no guarantee that these future... Yes.
I think, can you increase the sound a little bit? I think some people said that the sound is a bit low.
Oh, I'm not sure how I increase the sound, because I know how to increase my own sound.
Okay, so I think maybe people can do it on their end also.
Yeah, I'm not sure that there is a volume. Let me see. Maybe you can guide me on this. Is there a volume?
Michelangelo, yeah, it should be in settings. So if you go to either preferences or some settings, then there is an audio on the left-hand side. And there should be both speaker and microphone volumes that you can control.
So select the microphone, same as system audio settings.
You can click on that, and there's also an input volume button just below that.
Yeah, microphone, but I don't seem to be able to modify this somehow.
Maybe this automatically adjusts microphone is
so
clicked.
I think maybe so.
Oh yeah, I removed these. Okay, yeah. All right. So how about that now?
Yeah.
Is it more powerful?
Yeah. Yeah. Okay. Sorry.
I bypassed. Okay. No, but that's fine. Of course. Yes. Okay, I can try to speak up more loudly. But is it okay on average?
It's quite good now. Yeah. Thanks.
Okay. All right. So I was saying we have to explain and we have to convince ourselves that indeed building such huge and very expensive facilities is a good way to invest our resources in the future. And I will spend the first part of this talk to go through the arguments that, in my view, fully justify and support the need and the desire to have the next generation of colliders following the LHC. So our next steps build on having important questions to pursue and creating the opportunities to answer them. But at the same time, as we go through this search for new physics, perhaps, we also want to be able to continuously add to our own knowledge, even in the context of the physics that we already know. So, what are these important questions? Well, we know very well there is the question of dark matter, neutrino masses, etc., etc. There are theory-driven questions, the hierarchy problem, the flavor problem, the origin of the fermion families, quantum gravity. So these are the questions, and they're common to all of the branches of high-energy physics. But what are the opportunities? Now, the point is that for none of these questions, the path to an answer is unambiguously defined. For example, let us take dark matter. Dark matter can be anything between very light fuzzy scalars at 10 to the minus 20 electron volts, all the way up to multi-solar masses, primordial black holes, going through WIMPs at the TeV scale, or axions or sub-GeV dark matter. So that means that we cannot imagine just one single experiment that covers all. We do need a vast array of experiments, and each of us has to decide what is the experiment that they like the most, and you decide to invest in a specific experiment sensitive to one of these potential scenarios. And of course, at the end of the day, it's only one experiment or one set of experiments that will find, that will discover what dark matter is. And neutrino, the origin of neutrino masses is very similar. Even for neutrino masses, the origin of a phenomenon could be anywhere between the electroweak and the grand unification scale. And there are still many things that we don't know about neutrinos. We don't know whether there exist sterile neutrinos. We don't know what is the size of CP violation, whether they are Majorana or not, what is the mass hierarchy, etc., etc. And even in terms of acquiring this additional knowledge that will help us find the origin of neutrino masses, requires completely different experiments, and which of these additional information will be key and crucial to help us understand the origin of neutrino masses, a priori we don't know. And also, we cannot say that one thing is more important than another. We cannot say that it's more likely that dark matter is a WIMP than that it's an axion. All of these are equally likely. The criterion of what is more important evolves with time, and it's certainly subjective. There was a time in the 80s, late 80s and 90s, in which grand unification was the big thing, and proton decay was the most important signal that experiments should be looking for. And now, of course, it's still being done, but it is not on top of anybody's list as a search for physics beyond the standard model. So, for most of this question, all of this question, it's not obvious how to proceed. There is one question, however, that has come up more and more strongly from the LHC, and that I believe appears to single out in a unique, well-defined direction what we should be doing in the future. Let me close the door because I have some work going on. Just 1 second. Loading some stuff under my window, so I have to close it. So, and this important question, in my view, is the question of who ordered that. And that, of course, is the Higgs potential, which we take it for granted. But in fact, it's not. And we really have to start appreciating the value of this very, very trivial question, because that is really set to define the future of collider physics. So to better explain and articulate this, let me give you one example, which is an example in which I compare the dynamics in the, say, in a gauge sector of a standard model, say electromagnetism, versus the Higgs sector. So electromagnetism pretty much follows from Coulomb's law. And Coulomb's law, you see, involves several parameters. There are the charges, they are quantized. Of course, they define that there is nothing magic about the value of a Coulomb, but that is just a definition. We measure it and that defines what the charge of the electron is. The fact that they are quantized is, is something that we can connect with fundamental principles. It emerges in theories where electromagnetism is embedded in a larger gauge group, because there are anomaly cancellations and there are algebraic constraints within representations that force charges to be quantized and to be related across the different particles. So this is not something arbitrary, it's something that once you measure the charge, what charges are and their relative quantizations comes out of something. The sign of a Coulomb potential is not arbitrary, it cannot be negative. It's positive and it's fixed by the photon spin. The power in the denominator in the power law is 1. And again, it cannot be 1.2 or 1.006. It's fixed by fundamental principles like gauge invariance, charge conservation, or the Gauss theorem. If we look at the same in the Higgs sector, the dynamics of the Higgs is determined by Witt's potential. And let's take the standard model potential. There are parameters, mu, lambda, and these parameters follow from nothing. For mu square, both the sign and the value are completely arbitrary. Of course, mu square has to be there has to be a minus sign in front, because otherwise we wouldn't have the symmetry breaking. But that is just a phenomenological observation. A priori, that sign could have been positive, and then, of course, we wouldn't have symmetry breaking. Lambda has to be positive because we want stability at large values of the Higgs field. But again, there is no symmetry that makes lambda necessarily positive. And lambda could be negative, and then we could have additional terms in the potential to stabilize its behavior. In fact, in general, there is no reason to have a square and a quartic. We could have any function of h squared. We could have the log of the square root of 1 plus the cosine of h squared. That would satisfy all of the symmetry properties. Of course, h squared plus h to the fourth is the expansion near the origin. So pretty much any function will have this local behavior, but that doesn't mean that this is following from any fundamental principle. And a good way to put this into context is to think about the historical example of superconductivity. Early on, superconductivity was understood in terms of a Landau-Ginzburg theory of phase transitions. In presence of a quartic potential for a bosonic order parameter with a negative quadratic term, then follows symmetry breaking. And all of the phenomenology of superconductivity can just be explained by these. Superconductivity had been discovered after the Landau-Ginzburg. We would be in a similar situation than the one we are in today. We have the standard model Higgs phenomenon. We discovered the Higgs. We are happy. But still, what we have is equivalent of a Landau-Ginzburg representation. And we don't have a deep understanding of the relevant dynamics. In the case of superconductivity, this came several years after, when BCS, Bardeen, Cooper, and Schaefer understood what was the underlying dynamics. So Cooper identified in electron pairs the underlying order parameter, and the dynamics that leads to this quartic potential follows from first principles, from the interaction of phonons according to the rules of electromagnetism and of quantum mechanics. In the case of the Higgs, we cannot do that. With the standard model, we don't have a framework in which we can calculate and show that the Higgs potential is a fundamental quantity. If we want to understand the origin of the Higgs potential, we have to go beyond the standard model. The standard model cannot explain that. And to the extent that understanding the origin of the Higgs potential is as important as understanding the origin of the Landau-Ginzburg shape of the potential inside the metal that leads to superconductivity, this is one of the fundamental questions that we should be asking today. So there are possible scenarios beyond the standard model in which the Higgs potential follows from principles. One could be a BCS-like scenario, like the Higgs is a composite object, and then its potential and its properties follow from the dynamics that confines, say, a couple of fermions into the Higgs field. In the case of supersymmetry, the Higgs is a fundamental field, but then, for instance, lambda, which is the Higgs self-coupling, is related to the gauge coupling. So the Higgs, it's not arbitrary, follows from supersymmetry, and the details of the Higgs potential follow from supersymmetry breaking, so that they have some more fundamental connection with underlying physics or symmetries. So these are examples of possible scenarios, and there are many more. There is another interesting connection, or in fact, difference between gauge dynamics and Higgs dynamics, and that's the decoupling of the high-frequency modes. If we look at electromagnetism, we have the Gauss theorem. The Gauss theorem tells us that it doesn't matter how far we are from a charge. If we take the flux through a closed surface, that defines the charge of the object independently of how big is the surface. So we have a natural decoupling between the small scales and the large scales. We can detect what's happening at very small scales by taking a measurement at large scales, and vice versa. Whatever happens at small scales, we cannot really, is not going to affect what we see at large distances, because we cannot instantaneously transmit information between very short and very large distances. So that's the essence of the Gauss theorem, if you want, and the normalization theorems of QED. In the case of the Higgs, the parameters that control its behavior at large distances are strongly affected by what happens at very, very short distances. The Higgs self-energy, as everyone knows by now, is affected by these quadratic contributions, which are proportional to the masses of the fermions or the masses of the bosons with opposite signs. So this is, and the larger are these masses, the shorter is the distance that we are exploring, the bigger are the contributions to the long-range behavior of the Higgs, its mass. And likewise, the Higgs self-coupling receives contributions at high energy that have opposite signs, depending on whether it's a boson or it's a fermion, and the relative sign of this contribution can lead to the change in the stability of the Higgs potential itself as we go to shorter and shorter distances, or vice versa, changing sign as we move from the highest energies down to the low energy. So this important sensitivity of the Higgs properties to a very, very high energy behavior of a theory goes under the name of a hierarchy problem. So the Higgs dynamics is sensitive to all that happens at any scale larger than the Higgs mass. In principle, this can be fixed. The Higgs dynamics at large distance scales can be protected from what happens at short distance scales, but in the standard model, this requires a very unnatural fine-tuning. This is what we call the hierarchy problem. So the problem can be solved if we introduce new symmetries, which typically means new particles that will decouple in a natural way the high energy from the low energy. And this is what we call the natural solution to the hierarchy problem. And also here there are many examples. There is supersymmetry, the stop quark, the pattern of the top quark will cancel the quadratic contribution of the top, extra dimensions, little Higgs, many different scenarios that have been introduced in the past, say, 20, 30 years in order to address this problem. As in the case of understanding the nature of the Higgs potential, to solve in a natural way the hierarchy problem requires the introduction of new physics. And therefore, trying to build PSM models of new physics in order to address the hierarchy problem was a natural way somehow of guiding the exploration of new physics, experimental exploration. And it was a natural way to define a potential physics program and search program for the LHC. The promise to discover supersymmetry early on, for example, came out of this. Of course, we haven't found any of these new physics that arises in this search for a natural solution to the hierarchy problem. And therefore, it could be that indeed our understanding of the basic properties of the Higgs is incorrect, and we really have to review our biases. So this question of who ordered that, where does the Higgs potential come from, again, becomes extremely important when we put it into the light of the hierarchy problem. And therefore also innocent questions like whether the Higgs gives mass also to the first and the second generation, whether the Higgs boson has flavor violation, for example. We cannot give for granted anything that pertains to the Higgs boson. What we've measured so far are very basic properties of the Higgs, which from the point of view, from the perspective of an effective field theory, and at the current level of precision of experiments, would be true for a huge range of BSM electronic symmetry breaking scenarios. So the Higgs behaves as a standard model Higgs because at the level of what we've been measuring, it cannot do anything else. It's just a matter of expanding in powers the Higgs potential and verifying that it behaves the way it does. So that means that we haven't closed the book. If anything, we've opened a completely new chapter of exploration that will be based on precise measurements of the properties of the Higgs. And then, connecting to what I was saying a few slides before, contrary to dark matter, contrary to the issue of neutrino masses, the only way in which we can explore the properties of the Higgs is by using colliders, because we know of no other way to probe the Higgs properties than to create the Higgses. So this is what singles out colliders as the unique way to address this set of questions. There are, of course, other important issues that emerge in the Higgs sector, whether there's only one Higgs or whether there are more, the flavor properties of the Higgs, the issue of parameter stability that I will not cover in great, in fact, no, I don't think that I will go through it at all. Issues whether there is a relation between the Higgs and electroweak symmetry breaking and baryogenesis or dark matter or even inflation perhaps. The question of what happens to the electroweak phase transition during the Big Bang. So there are many additional open questions about the Higgs that we need to address and for which there is absolute need for a collider program. And to the extent that only a fraction of these questions hopefully can be answered by the LHC, this clearly leaves open a huge range of opportunities and needs for future colliders. So as we approach these future facilities and we try to define what their somehow potential should be, we have to start from this important question, which is why don't we see the new physics that we expected to be present around the TeV scale? Why don't we see it as yet at the LHC? And there are two possible answers. One is maybe the mass scale is beyond the LHC, which we haven't seen supersymmetry because neutrinos and quarks, they're all at 4 TeV, and we still don't have sensitivity to 4 TeV. But maybe the mass scale is actually within the LHC reach, and we are producing these objects all the time, but the final states of this new physics are elusive to our direct research. And a priori, both of these are equally likely. So if we really want to build an important facility for a long-term planning for the long term, we have to make sure that we can cover both of these possibilities And to do that, we want to make sure that we have an extended energy and mass reach in case the mass scale is indeed beyond the LHC reach. And we want to improve the precision, and we want to improve the sensitivity to possible elusive signatures. Now, there is no way that we can build a collider guaranteeing that a specific discovery will be made. But this is not only a problem of colliders. This is really a problem of any possible future facility in high energy physics. So this remark that you see here, we have to, whenever we discuss the future of our field, we have to have very, very clear in our mind that there is no experimental facility that's been proposed or that is conceivable, whether in the lab or in space, accelerator or non-accelerator driven, that will guarantee discoveries and will guarantee answers to the big questions. So we cannot judge the value of facility on the basis of what it is that it guarantees in terms of discoveries. What we can do, however, is to weigh criteria such as, for example, guaranteed deliverables, namely, what will I learn from this new facility, no matter what? What can I guarantee that, what's the progress that this facility will guarantee? This is knowledge that will be acquired independently of possible discoveries, and it's all related to the ability of performing concrete measurements. Of course, you want to have an exploration potential, and that means you just look at very at a broad set of justified, reasonable BSM scenarios, and you want to make sure that those will be covered. And of course, you want to make sure that you will be covered also if what turns out to be the new physics, you have not thought about it. You have to be enough flexibility to cover more exotic options. And then, of course, you want to exploit as much as possible both the possibility of directly discovering something like a new particle by producing it, or being sensitive to the existence of new phenomena through indirect, for example, precision measurements. And finally, it would be nice to be able to provide conclusive yes and no answers to important questions. People often ask, yeah, but you know, if you go to 100 TeV, will you be able to exclude categorically supersymmetry? Well, that is not a question that can be answered in a conclusive way. Of course, if SUS is there and is discovered, then yes, we can conclude that it exists. But if no sign is seen, one cannot exclude categorically that it's not there, because one can always argue the mass will be slightly larger, or maybe there will be a different realization of supersymmetry breaking, but again, 100 TeV is not enough. So this would not be a good question which admits a yes or no answer, but there are other important questions for which a next facility may be able to give a conclusive yes or no answer. So when we put these three criteria in the context of the future circular collider, where the guaranteed deliverables are the ability to study the Higgs and the top quark and to explore the dynamics of electronic symmetry breaking with a precision that is completely superior to any other possible facility. The exploration potential is guaranteed by the extended mass reach that the 100 TeV proton-proton machine can give, as well as by the precision that the plus and minus studies can offer. And finally, yes and no answers that could receive a conclusive questions that could receive a conclusive answer are, for instance, whether dark matter is a thermal WIMP, because thermal WIMP cannot be arbitrarily heavy, and a 100 TeV machine could, in principle, completely close the upper limit on the mass of thermal WIMPs. The question of whether a cosmological electroweak phase transition has been of first order or not is again a question that, in principle, does not admit solutions of particles of arbitrarily heavy mass, because the electroweak phase transition was not what predicted by the standard model, which is a very smooth crossover. this requires the presence at a mass scale around the electroweak phase transition, so around a few hundred GeV. There has to be new physics there to modify the properties of the electroweak phase transition. And again, a 100 TeV machine and the precision given by plus and minus in principle can answer this. So these are just some examples that are relevant. So in the remaining of this talk, I will give a few concrete examples of the physics potential. I will focus on the 100 TeV case because I looked at my Corazzino slides and we spent a bit more time discussing E plus and minus, but I will also say something about E plus and minus. So I will start by giving this table, which is event rates at the different facilities, V plus and minus, the HH, the 100 TeV collider, and the EH, event rates for the planned integrated luminosities and for several interesting final states. For example, the plus and minus collider can deliver, it's about 1 million Higgs, is 5,000 billions, 5 trillions of Z bosons, 100 millions of Ws, millions of top quarks. The Hadron Collider has statistics which are much, much bigger, 25 billion Higgses, so a factor of over 10,000 more than the plus and minus, but of course the experimental conditions are not as good as they are in the plus and minus. 10 to the 12 top quarks, which provides immense opportunities. And now we go through several processes, and these numbers will come back again, but this is just to give a quick overview. So let me start from of these three main criteria: the guaranteed deliverables, the discovery potential, and the ability to give conclusive yes or no answers. I start from guaranteed deliverables and I start from the Higgs. So what sets the scale for the precision with which we want to know the Higgs properties? This is a table from a rather old assessment of the impact on modifications of the Higgs couplings. What you see here, kappa V, kappa B, kappa gamma, these are the effective couplings of the Higgs to vector bosons, so WW or ZZ, to the B quark or to the gamma-gamma photon pair. And, and for different models of new physics, this is the size of the effects that in principle one could have consistent with other direct constraints on this collection of models. So you see, we're talking about the percent level. There are exceptions. Here deviations can be large, like 10%. Here deviations are very, 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 very small. But typically for interesting models, we are talking about the percent. So that means that if we want to have evidence for 3 sigma deviations from the standard model, we must have as a precision goal below the percent level. Now, E plus E minus has a unique feature that cannot be matched by any other collider independently of the statistics, and that is the ability to allow a completely model-independent measurement of a total width of the Higgs, and therefore a completely model-independent measurement of some absolute branching ratio. This I know that was discussed by Mike last time, and this is something which is well known. The Higgs produced in association with the Z, since the Z decays to a fully reconstructible final state, in principle one can measure directly the so-called missing mass, which is looking at the momentum of the initial state, which is known because these are the beams, minus the momentum of a Z boson, that's equal to the momentum of a recoil system. And if we take the momentum square, we get the mass of a recoil system. And if we plot the mass of the recoil system, we will see a big peak, which is the Z boson in the case where we have ZZ production. But then the contribution of the Higgs will manifest itself as a peak corresponding to the Higgs mass. And the height of this peak is completely independent of our ability to reconstruct the Higgs boson, because we're not looking at the Higgs boson, we're just looking at the recoil. So this is a measurement which is absolutely unique to E plus and minus, and by itself justifies the E plus and minus Higgs factor. What is unique about the Hadron Collider in the context of physics are the huge statistics. As I said before, several billions, and here in this table you can see it for the different production channels. In addition to the statistics, one also has a huge dynamic range in the production. If we go to the next slide, this is the total number of events expected at 100 TeV during the lifetime of the experiments. This is the total number of events of Higgs produced with a PT of a Higgs larger than a given threshold. For example, if we take 1 TeV, you see we're talking about over 1 million Higgs bosons produced with a PT larger than 1 TeV for the glue to Higgs final state, or for the TT plus Higgs, the associated production of the TT bar and a Higgs boson. And you see the rates extend all the way up to several TeVs. And this, of course, has big implications, both in terms of the way that the analysis will be done, but also in terms of sensitivity to dynamics of the Higgs that involves very, very high scales. So when it comes to doing, say, EFT, effective field theory analysis of the Higgs properties, getting access to virtualities, being able to probe the Higgs with off-shell probes at the scale of several TeVs becomes extremely, extremely important. So we have 3 kinematic regimes for the Higgs which are interesting. One is the inclusive production, so all Higgs is PT larger than 0. The rates, of course, are huge, but in this machine are extremely challenging because if the Higgs is produced at rest, the final state is 20, 30, 40 GeV particles or objects, so they're very hard to measure in a context of very large pileup. So it's very challenging even to do the detector simulations. Presumably today detector simulations are rather unreliable. So this regime of inclusive Higgs production is not being studied so far in the case of the FCC. In other words, the LHC, all of the analysis of the LHC, they try to capture all of the possible Higgses that are available. Say Higgs to gamma, you just look at all of them. And here we're not trying to do that. There are so many Higgses that one can afford just looking at Higgses produced in situations where hopefully the experimental analysis will be simpler. And that is the range where the PT is slightly boosted, say PT of the Higgs above 100 GeV. Here there is still plenty of statistics, as we will see. The signal to backgrounds are significantly improved. One gets into a region where the trigger thresholds are acceptable, and the extrapolation of detector simulations from, say, the high luminosity LHC studies are more robust. And this is the regime, the range of the PTs in which we focused our study of the Higgs in the FCC documents. And finally, there is this regime of multi-TeV production, where the statistical uncertainty is still at the level of 10%, all the way up to 1.5 or 3 TeV, depending on the decay channels that we use. For example, we can have a 10% statistical precision of the measurement of Higgses going to BB bar with PTs larger than 3 TeV, so very heavy objects. And here, this offers new opportunities for the reduction of the systematics, but also, as I said before, it offers new opportunity for indirect sensitivity to BSN effects at very large Q squared. So again, impact on EFT interpretations of the results. And this slide is just one example. This is the rate of Higgs goes to gamma gamma as a function of the minimum PT of the Higgs. These are number of events. So above, say, 200 GeV, we are talking about almost several hundred thousands of events. The solid line is the signal, while the dashed lines and the dotted lines correspond to the QCD backgrounds. So as you see, what is interesting when you look at the right plot, the window on top, the highest window, that is the signal to background. And you see that at small pt, signal to background, the Higgs signal over the QCD background, is only a few percent. But as we go to very high pt, already above about a couple of hundred GeV, signal to background becomes of order 1. So if you see a pair of photons with a mass around 125 GeV at 100 GeV, it's more likely to be a Higgs than it is to be a QCD diphoton pair. So this makes the analysis much more straightforward. And this is, as you see, we have a statistical precision on the level of 2 per mil if we can take Higgs is above 100 GeV. So these studies were done for these rare final states of Higgs to gamma gamma, Higgs to 4 fermions, Higgs to mu mu, and Higgs to Z gamma, with Z going to mu mu. These are all processes with branching ratios below 10 to the minus 3, which means that with the 1 million event statistics of a plus or minus Higgs factory, one would not be able to match the 1% threshold for the precision. If we have 1 million event, you need a branching ratio not smaller than 1% if you want to have 10 to the 4 events and therefore a 1% statistical precision. In order to go down to 1%, if you have a branching ratio 10 to the minus 3 or 10 to the minus 4, you need hundreds of millions of events, and that's what the Hadron Collider will do. So looking at these ratios, the ratio of the Higgs to gamma gamma, for instance, over Higgs to E plus E minus, mu plus mu minus, allows the Hadron machine to reduce significantly both the theoretical and the experimental systematics, because it's a ratio, so the luminosity, many of the identification efficiencies drop out, and certainly the theoretical uncertainty on the production rates of the Higgs goes away because we are taking a ratio. And by having a very precise measurement of the Higgs coupling to the Z, which comes from the precise measurement of Higgs Z production E plus E minus, that provides this denominator, which is very precise, and therefore we can extract the absolute branching ratio of the Higgs to gamma gamma by looking at the measurement of these ratios. And as a function of the PT mean of the Higgs, you see the green is the statistical uncertainty, and these two yellow and red lines correspond to different scenarios for the systematics. The optimistic one has a minimum at about 200 GeV. That says indeed that operating in this regime of slightly boosted Higgses provides the sweet spot, an optimum compromise to optimize the precision. So it's important to notice that these ratios of branching ratios are by themselves quite interesting, even if we didn't have the absolute benchmark of Higgs to ZZ. Because if there are alterations due to new physics, with the exception of new physics that shifts the total weight of the Higgs, but then if it's new physics that affects individual couplings, it's very hard that it will maintain something like the ratio of branching ratios of Higgs to gamma gamma and Higgs to ZZ, or Higgs to mu mu and Higgs to ZZ, or Higgs to invisible and Higgs to gamma gamma, just because these are completely different processes. Higgs to invisible means that we are talking about something which is neutral because it's invisible. Higgs to gamma gamma requires in the loop, obviously, the presence of something which is charged. So it's completely different physics that will affect these two. And therefore, measuring very precisely these ratios could be a sensitive way of disentangling the presence of physics. So, this systematic study of analyzing from a theoretical, phenomenological perspective these branching ratios in the context of new physics models, this is something that is work that needs to be done. It's not being done in a systematic way. It would be nice to have precise guidelines from the study of specific models as to how precisely we need to measure, say, the ratio of Higgs to mu and Higgs to ZZ, or Higgs to gamma gamma and Higgs to Z gamma to sort out different BSM models. I have a few slides here on how we study the case of the Higgs coupling to the top, the Yukawa coupling of the top, but I can go through that and jump directly to this table, which is a summary of the precision of Higgs couplings after the FCC EE and HH. And as you see, for the states which are accessible to the E plus E minus, the precision is indeed below the percent and goes down to the level of 2 per mil in the case of the coupling of the Higgs to the Z boson. But then for processes like Higgs to mu, Higgs to gamma gamma, Higgs to Z gamma, or Higgs TT bar, we see that the plus E minus machine cannot do it, but then we go below the percent level by using the HH results. There is further work that can be done if any of you is interested in contributing. For instance, we haven't thought about how to measure at the LHC the total Higgs width. There are techniques, of course, that have been proposed for the LHC and that are being used. The LHC is already setting limits on the total Higgs width. Trying to think about these techniques or others in the context of 100 TV has not been done, and I would be happy to see work. We haven't considered the channels with a large branching ratio like BB, WW, tau, tau. We will not improve, the Hadron machine cannot improve what the plus and minus machine can do, but if we know and if we learn how to work with Higgs to BB, WW, and TT, then we can use the Higgs as a tool, for example, to get to much larger values of PT Higgs. Probes of the Higgs to charm coupling have not been studied. For example, exclusive Higgs to J-psi photon decays have not been studied at 100 TeV, and this is also work that could be interesting. And of course, couplings to lighter quarks as well. Also, the study of the possible discovery of sensitivity of Higgs flavor changing decays, like Higgs to mu, mu tau, e tau, or other multi-body decays have also not been done. And it would be nice to see work being done in this direction. I don't have much time left, so I will skip the discussion of the high Q-square behavior and the precision versus dynamic reach in setting constraints on the operators. We can come back to these if there are questions, but let me move on. Guaranteed deliverables, electroweak observables, of course, in addition to the Higgs program, there is the electroweak program that is only possible at the circular plus and minus, while the Higgs can be done also by a linear plus and minus collider. If we want to have the statistics of 10 to the 12 Z bosons, this cannot be done in a linear plus and minus collider. This absolutely requires a circular plus and minus collider. And this provides improvements by a factor of 10 to 100 in the precision with which all of the electroweak observables and standard model parameters are measured relative to a factor of 10 to 100 improvement relative to LEP or relative to the current knowledge. Here also the Hadron Collider can help. For example, there was this recent determination of lepton universality in the decay of the W, the comparison between W going to tau branching ratio relative to the W going to mu or a lepton branching ratio. LEP finished LEP2 leaving a 2.5 sigma disagreement with lepton universality, using the W's in TIFR case, of which there are plenty in Atlas, and there will be at least 100 times more, in fact, much more at the FCC, was able to prove that, in fact, within less than 1 sigma, universality is established in W decays. The discovery reached at high mass. Well, in principle, it's quite easy to extrapolate what we know already from the LHC, because if we look at high mass, we know that 100 TeV is 7 times bigger than 14 TeV, so you can take all of the limits that the LHC has been able to obtain so far, you multiply by 7, and that pretty much will give you the reach, or the discovery reach, or the exclusion potential of a 100 TeV collider. These very high mass signatures are relatively straightforward to identify experimentally, and so this doesn't really require much work. Work has been done, nevertheless, to verify that indeed the detectors that the experimentalists are designing for the FCC are suitable to do these measurements in the multi-TeV range. And this table, for instance, is the result of the detailed Delphi study of the discovery potential for S-channel resonances, like excited quarks to digits, or Z primes going to TT bar, Randall syndrome gravitons going to W plus W minuses, and the standard Z prime going to dileptons. And you see the mass scale is in the range of between 20 and 40 TeV, depending on the channel. Supersymmetry, one should be able to get to stop quarks up to about 10 TeV, and gluinos in the range of 15 to 20 TeV, depending on the mode. In this case, 10, 20, 30 TeV happen to be consistent with the scales that precision measurements of electroweak and Higgs observables at plus minus of possible scales at which deviations from the standard model can be observed. So the indirect precision measurements of electroweak and Higgs observables at FCC AE are sensitive to scales which, as you see in this plot, go up to 20, 30, 40 TeV, and that is the range in which the 100 TeV machine could perform the explicit discovery. So as for this issue of potential to answer yes or no questions to important issues, well, let's take dark matter, for example. This is what I mentioned before. There are fundamental theoretical constraints that tell us that the mass of the WIMP, so a weakly interacting massive particle that is responsible for thermal production of dark matter, has to be limited by 2 TeV times the square of its coupling. So if we put in the coupling of a doublet or a triplet or a singlet, well, a doublet or a triplet, say, of electroweak particles, we get numbers that range between 1 and 3 TeV. So this would cause a Chargino in the case of a triplet versus 2, and a Higgsino in the case of a doublet. So this red band is the discovery potential at you see as a function of, well, as a function of the mass of the object. The dashed line is a famous 5 sigma. As you see that 5 sigma for, say, the triplet for the Wino-like dark matter goes all the way up to about 5 TeV. And in the case of the Higgsino, it goes up to about 1100 GeV, which means that indeed one would surpass this thermal mass range, and therefore either you see it or you don't. And if you don't, it cannot be there, it cannot behave on that. And therefore one could move to other dark matter scenarios and forget about these thermal WIMP categories. It's time for me, I guess, to wrap it up. I also had some considerations about the nature of the weak phase transition. I can come back to this in the discussion if there is interest, but otherwise I go directly to my conclusions to finish in the 1 hour. Final remarks. I spent a lot of time trying to convince you that we cannot be happy with what we have today. The understanding even of the standard model cannot be complete until we clarify the nature and the origin of the Higgs potential and the Higgs mechanism. So there are many aspects that are obscure. Many questions are still open, and more in general, really the very question of where does the Higgs come from, independently of the problem of naturalness and the hierarchy problem, but understanding where does that potential come from, why is mu squared negative, is a fundamental question that we have to answer. The combination of a versatile high luminosity plus and minus circular collider, versatile because it can operate at many different energies, so it goes from the electroweak factory at the Z peak all the way up to the TIFR threshold. The combination of these with a follow-up collider in the 100 TeV range appears like the ideal facility for the post-LHC era. There is nothing of these power, of these physics potential that is possible to conceive today and that can be realized with the technology that we know. The two machines are complementary and synergetic in the studies, in the precision studies of the electroweak, the Higgs, and the top properties, and the energy reach of the 100 TeV, of course, allows for direct discoveries at the mass scales that could be possibly revealed by the precision measurements. So this is the same way that LEP and LHC complemented each other. It's absolutely clear that this is the facility that will provide the best hopes for the discovery of new physics and certainly for completing in more detail our understanding of the standard model. Thank you.
Thank you, Michelangelo. I think the floor is now open for questions. So now you don't even need to raise your hands. Just if you have a question, just go ahead. So I'll wait a little bit. I do have a question. So let me ask mine first, and maybe we'll have some others. So you made the statement that either we didn't see any, one possibility is we didn't see anything at the LHC because the energy of the particles was a bit higher than its reach, or there is a possibility that the detector was not sensitive to the specific new physics that is present. So I think maybe one thing is this degenerate cases of excited states. Now, so I wonder if that is, I mean, should we think a little bit more about that question in the sense that if that is the issue, then that will be an issue also for a 100 TeV machine, right? Just going higher in energy will not get rid of that issue, or there are techniques which you can use in that case.
No, well, there are two parts in this answer.
Okay.
One element in the second bullet is also the possibility that the mass is small, but the physics is very, very weakly coupled.
Mm-hmm.
So we don't see because pretty much we don't have enough events. So it's a signal to background issue. So for that, we need much more statistics. And the 100 TeV machine with a higher luminosity would provide much higher statistics. So that's question number one. Point number one. And point number two, there is this issue of being able to access higher, say, PTs, more extreme kinematic configurations. And typically, whenever we go in these selected corners of phase space, I mean, we can find selected corners of phase space in which we enhance the signal to background. And I can give you hundreds of examples of this. For example, the physics of the top quark at the tevatron was very hard to do because there was a lot of background. It was very hard to pull out the top signal. At the LHC, it's enough to require that the top be boosted, so you require the final state to have jets with PT larger, let's say 4 jets with PT above 150 GeV, plus electron, and automatically the signal to background, TT bar relative to the W plus jet backgrounds, become of order 1. I gave you the example of Higgs to gamma gamma. If you look at the inclusive Higgs, the signal to background is 3%. If you take at the Higgs above 200 GeV, signal to background is 1 to 1. So this additional kinematic reach can also help significantly in this in sorting out these different difficult signal to background situations. But of course, it has to be seen case by case. It has to be looked at case by case.
Okay, yeah, thanks. Any other questions? Yeah, so Rajiv has a question. So, yeah, go ahead. Share.
Hi, this is Rajiv Gawai. You made a statement that one should have a well-justified beyond standard model for making the second part of your goals or satisfying that. On the other hand, your 100 TeV collider is only going to increase the existing bounds, for example, in SUSY by a factor of 2 or 3. Is that really a well-justified BSM?
No, I said it's not that we need a well-justified BSM. I said that we use, you want to make sure that all of the well-justified BSM models are covered. So you use well-justified models as a way to build your exploration of the physics potential. Okay. Now, for what concerns supersymmetry,
in another way, if you don't mind.
No, but let me answer. Let me finish to answer. What?
No, I think on page 19 you said well-justified model, BSM model, and in the end it doesn't look like there is any well-justified BSM model that will be tested by the FCC HH.
No, I don't understand. For example, you said that SUSY would be improved by a factor of 2 or 3. No, the SUSY limits will be improved by a factor of 5, much more than that. In the case, for example, of the electroneutrinos that I was mentioning, like for dark matter, the fact that you can improve the mass limit on a Rhino or a Higgsino by a factor of 5 is absolutely crucial in order to tell whether they exist and they can be dark matter or not. So a scenario where the Higgsino is a dark matter candidate, the LHC cannot rule out, and even just increasing by a factor of 4 or 5 the mass reach allows you to completely explore or to completely exclude that possibility. So it's more than just improving by a factor. It can be determinant in ruling out and fully exploring possible scenarios.